So calculus studies how functions on the real line change. And we're going to talk about one idea of how functions change that should be relatively familiar to you, and that's the average rate of change. So what is that? Now I'm going to start with a function. So f is a function, and this function has a domain, but I'm not really going to mention the domain so much right now, because I'm going to assume everything I'm talking about is occurring within the domain of the function. Okay, so f is just some function. Maybe it's x squared, maybe it's a line, doesn't matter. This is something I can define for any function. So the average rate of change of my function now it's the average rate of change of my function over an interval. Now that's very important. Over some interval, which we'll just denote as a closed interval from a to b. So this could be like the interval from 0 to 1, 1 to 2, -1 to 1, I don't know, any interval. Now the only condition I need is, of course, that this interval be contained in the domain of the function, but we're going to assume that's true. So the average rate of change of this function over an interval is, well, it's pretty simple. It really is just like the rise over run. So it's the change in the function values. So it's f of b. So this is like y2 minus y1, if you remember that idea from the slope. So f of b minus f of a divided by the length of the interval, b minus a. So this is the average rate of change of f over the interval ab. And now we'll see that I told you this is something that you've seen before. And so if you think about this function as being the position of your car, and this interval being actually a time interval, then this average rate of change is actually your average speed. So hopefully that connects with you where we're going with this. So we have a function, we have an interval, we're just seeing what is the average rate of change, like the velocity or the speed in your car, something like that. Now this is not the instantaneous rate of change. This isn't what I'm reading off of my speedometer in my car. This is my average speed over some time interval. So if I travel 30 miles over the course of an hour, my average speed is 30 miles per hour. Now my speed may have fluctuated between there, but this is really the average. So over that hour, or however long, whatever the interval is, the average rate of change, or the average velocity, if you like that example, is given by this. Now, there's also a geometric way to view the average rate of change. So suppose that the graph of my function looks something like this. Okay, there's my function. So the average rate of change of the function, let's say that here's a and here's b. So remember the interval lives in the domain of the function. Then here's f of a and here's f of b. So here, now this is in the y direction. Now sometimes I'll be lazy and not label the axes, but here I'll make it clear this is the y-axis and the x-axis. So this is f of a, and this is up here f of b. So now notice this isn't a line, but it really is like rise over run. So it's saying over this interval, I'm increasing this much when I go over the entire length of the interval. Now these two lines, these 2 points, getting ahead of myself, actually form a unique line. So if I just kind of connect the dots here, let me try that again. Well, you get the idea. Like that, I get a line. So 2 points in the plane give me a unique line. Now notice that this rise over run, or this average rate of change, is the slope of this line. Now this line has a special name. It's called a secant line. And a secant line passes through 2 points on a function or on a curve. So this is a secant line. So another way I can think about the average rate of change, so the average rate of change is the slope, not of the function, because that may not really make sense, because the slope of the function is actually changing at any given point, but it's the slope of the secant line. Passing through these 2 points. So the points A, f of A, this point, and B, f of B. So that's a really nice geometric way to view the average rate of change. It's just the slope of the secant line. If you like the real world application way to think about it, it's the average velocity. It's how much I've gone in some amount of time. So there's lots of different ways to think about average rate of change, just like there'll be lots of different ways to think about just rates of change in general, or how functions change in calculus. And we're going to try to highlight as many as we can so you can see a lot of different perspectives. So we've talked about the average rate of change of a function. Now a key thing to remember is that the average rate of change is over an interval, because now we're going to transition and talk about the instantaneous rate of change. So instantaneous. And still, f is some function. Okay, it has a domain. I won't really mention anything about the domain, but what I talk about the function is going to occur within the domain. So what is the instantaneous rate of change? Well, right now we don't have a very precise way to say what the instantaneous rate of change is. But I don't think the precise way of saying what this is helpful to understand what it really is. So recall that I mentioned with average velocity, so if you like that analogy of average rate of change of a position function being the average velocity, so that's the average velocity over an interval. So the instantaneous rate of change of f, not over an interval, but at some point x equals a in the domain of f, is like the instantaneous velocity or the instantaneous speed. So at any given time, the instantaneous rate of change is what your speedometer is telling you how fast your car is going. Okay, so let's think about this in terms of a picture. So recall if we have a function, so let's just draw some function that we're looking at. If you like, you can think about it, it's the position of a car at a certain time, something like this. Okay, and so remember, if we had an interval, we could find the average rate of change, or the slope of the secant line. But now we really just want to consider one point, A. And so if we plot our point, up here will be f of a on the y-axis. And so the instantaneous rate of change is, now remember that picture, if I zoom in, so let me just zoom in over here. If I zoom in close enough, then my function really will look like a straight line right here, if I zoom in close enough. And so I can just find the slope of that really, really small piece of the line, okay? And that slope is going to be the instantaneous rate of change. And this is actually how cars figure out the velocity. What they really do to give you your actual velocity is they measure an average rate of change over a really, really small interval to find the instantaneous rate of change. How fast am I going at this instant? Not an average over an interval, but at an instant. Or if I look at this function, what is the slope of this function at this point? So you see that at this point here, the slope is going to be negative, so the function is decreasing. And then here it's leveling off. And then over here it's actually increasing. So the point we're considering, it looks like the slope of the function is positive. Now we're throwing out this expression slope of a function. We're going to be a lot more precise later. But for now, we just need to get a feel for what the instantaneous rate of change is. And so hopefully I've given you a few ways to think about it. The last way to think about it, recall that the average rate of change was the slope of the secant line passing through 2 points. Well, the instantaneous rate of change is going to be the slope of the tangent line. And now what do I mean by tangent line? Well, the tangent line is the line that passes through that point, AF of A, but that's the only point in that small little window that the tangent line hits. So it just barely grazes the function like that. So this is the tangent line. Now it's not the tangent line between 2 points, it's the tangent line at x equals a. And so then we can reinterpret what the instantaneous rate of change is. The instantaneous rate of change is the slope sort of the function, but that doesn't really make sense right now. It's the slope of the line tangent to the curve. And now by the curve here, I mean the curve that is the graph of the function f. So hopefully this gives you a couple snapshots into the 2 different types of change we can talk about. We can talk about average rate of change of a function over an interval, and instantaneous rate of change of a function at a point. Secant line versus tangent line. Average velocity versus instantaneous velocity. All right, so let's get our hands dirty with this average rate of change versus instantaneous rate of change, and hopefully start to see the bigger picture. So here, our function is x squared, and our goal is to find the equation of the secant line passing through the function at x equals 1 and x equals 2. Okay, so notice that we're looking for the equation of a line. So to find the equation of a line, this is great pre-calculus review, we need 2 things. We need the slope of the line, and then we need a point on the line. And then we can use what's called point-slope form. Now, you can also use what's called slope y-intercept form, but the y-intercept is kind of a more rare thing to have. It's more likely that you can find a point on the line and the slope of the line. So I like to always use point-slope form. And in fact, slope-intercept form is just a special case of point-slope form. So let's get our hands dirty. How are we going to find the slope? Now the equation of the line we're looking for is this secant line. So recall that the slope of a secant line between 2 points or over an interval. Now notice that my interval here is going to be 1 to 2, right? Because it's the secant line passing through the points 1 and 2, is going to be, okay, so the slope is going to be the average rate of change of the function over this interval. So in other words, it's going to be f of 2 minus f of 1 divided by 2 minus 1. That's the equation for the average rate of change of a function over an interval, which is the slope of the secant line. Okay, so what is this? Well, f of 2 is just 2 squared. So 4 minus 1 divided by 2 minus 1 is, okay, 3 divided by 1. So 3. So the slope is 3. Now we need a point on the line. And here we actually have two choices. We can either use 1 comma f of 1 or 2 comma f of 2. So I'm just going to use 1 comma f of 1. And now f of 1 is really 1 squared, which is 1. So my point on the line is just 1 comma 1. Okay, so what does point slope say, just to remind you? Well, it says y minus y0, where y0 is a point on the line, is the y-coordinate of the point I know on the line, is equal to the slope times x minus x0, where x0 is the x-coordinate of the point I know on the line. So n, that's the slope, so in this case the slope is 3. So my final answer is y minus the y-coordinate of the point I know, so minus 1. And then the slope is 3. And then x minus the x-coordinate of the point I know on the line is 1. And I can actually simplify this out. So if I write it actually in slope-intercept form, I get y is equal to 3x minus 2. So this is my equation of the secant line passing through the curve or the graph of f of x at x equals 1 and x equals 2. And on the next slide, I'm actually going to show you a graph of the function along with the secant line. All right, so here is a graph of our function. F of x is equal to x squared. And here's x equals 1, so there's f of 1. So here's the point 1, 1. That was our first point. And then here's 2, and up here is f of 2, which is 4. So this is the point 2, comma 4. And what we found, the equation of this line, recall that it was y equals 3x minus 2, is just the line passing through these 2 points. Now the significant thing to remember is that the slope of this line has a very important interpretation as the average rate of change of this function over that interval. So even though you'll see that at times the function looks like it has a slope less than this curve, than this line, and at times it looks like it has a slope greater, sort of the average of all those slopes really is 3, the slope of that line. So this is the secant line passing through those 2 points its slope is the average rate of change of the function. That's the idea. Okay, so this is a really cool application, and it's something I hinted at, and it's going to make the connection between the average rate of change of a function and something you're maybe more familiar with, average velocity. And I really like these physics applications because they kind of give a real-world, concrete way to think about these abstract concepts we're going to be defining in calculus. And so here, s of t is a function. Now we've written the independent variable is t, just to specify that it's changing with time. So this function, which is the position of where you are on the road, is the dependent variable s, depends on the independent variable t. That's the idea. Okay, so this notation, it's common to just use s of t for position as a function of time. Now t is in hours, so these are just all things I'm noting. Okay, so after 1 hour, you've driven 40 miles. So like it says here, that tells us that s of 1 is 40. And then after 3 hours, you've driven 200 miles. So s of 3 is 200. Now I'm actually going to draw a picture to try to make this a little bit clearer. I'm not very great at drawing pictures, but from time to time, it really helps, right? Because this is a real situation. So let's say I start here. So this is t equals 0. And I'm driving down the road, down the interstate, or down the highway, whatever you want to call it. And so I know, on one hand, t equals 0. I've, of course, traveled 0 miles, right? Because I haven't started yet. T is 0. But after 1 hour, so at t equals 1 hour, I've gone, so this distance here is 40 miles. Okay? And then later, after 3 hours, I've driven 200 miles from where I started. Okay? And so, of course, t is in hours, s is in miles. So this sort of double number line idea is a great way to visualize what's going on. And I'm not going to draw the car, but your car is just moving along like this. And so probably if I asked you, what is the average velocity as you drive from this point to this point, you would probably be able to tell me. But what it is it's just the average rate of change of this function. So s of 3 minus s of 1 divided by 3 minus 1. And now remember, I'm just looking over this time interval between hour 1 and hour 3 of my trip, wherever I'm traveling. And so what is this? This is 200 minus 40 divided by 2, which is 160 divided by 2, which is 80. And now at my units here, I'm taking a difference of a number of miles and dividing by a number of hours. So my units are miles divided by hours. But that, of course, has a more common name, miles per hour. Like that. So my average rate of change of my position function is 80 miles per hour. And now we've already mentioned this, but I want to nail this point home, that this really is the average velocity. And something we'll see later is that velocity really is how a position function is changing, whether that's an average velocity or an instantaneous velocity. So hopefully this helps you get the picture of what the average rate of change is. So before we get too deep in the mud and kind of get into the gory details, let's just stop and think about some other applications that we may encounter in calculus. And so I told you that calculus was really about how functions are changing. But a function is an abstract thing is not very useful. What a function really should be doing is modeling some sort of phenomenon in the real world. We've already seen one great example. The position of a car is a function, and we can study how that function changes in the form of the velocity. That's kind of the stepping point to calculus. But there are plenty of other functions that model other phenomena in the real world. So let me give you just a couple silly ones that hopefully start to get your mind turning and thinking about where calculus can be applied. And you'll be surprised because the answer is that calculus can be applied all over the place. So let's look at some other functions, and we'll give an interpretation of the average rate of change. So my first one that I'll tell you is k of t. And here, k of t is the number of kilobytes, so it's kilobytes, downloaded after t seconds. Okay, so I know that we're kind of in the age of super fast internet, but back in the good old days, when you would download a file, a little box would come up and it would say 2 hours and 45 minutes left in the download. I mean, this would just be like trying to download Oregon Trail or something, I don't know, but it would take forever. And you would sit there and think, how fast is this really downloading? It had a download rate, and so that's kind of what this is. And so k of t is just how many kilobytes have been downloaded after t seconds. So let's interpret what the average rate of change is over some interval. So the average rate of change, which I'll abbreviate average rate of change, AROC, is the average download speed. So obviously, the faster your internet is, the faster your average download speed is. And the units here are going to be kilobytes per second. Okay? So if you have super fast internet, now, and maybe they even talk about millibytes per second. Sorry, not millibytes, megabytes per second, because it's so fast now. I would guess that probably things are downloading a lot faster than 1 or 2 kilobytes per second, so it's probably up to megabytes per second. Maybe in our lifetime it'll be gigabytes per second. We'll be able to download even faster than we have before. But that's just an example. So another example, this one is from biology. So h of t is the height of a plant t days after it was planted. Okay, so let's interpret the average rate of change. And so here, okay, so my plant is growing. So its height is given t days after it's planted. So of course it's going to start with height 0, and it's going to stay 0 for a while. And then all of a sudden it's going to jump up, and then its height is going to be increasing. And then maybe it actually gets to a certain point and it starts to wilt, and then the height of the plant might be decreasing. I don't know, something like that. Okay, so what is the average rate of change? Well, it's the average growth rate of growth. And so let's say that the height, let's give the height units. So maybe the height is in centimeters. So then the average rate of growth is going to be in centimeters per day. Okay, so it's just a rate of growth, average rate of growth. So these are just a couple of examples. I'm sure you can think of a lot more, depending on what you're kind of going into, what you're looking to be when you grow up, so to speak. You can think about other examples of functions and how they change and kind of interpret what is the average rate of change. Okay, so this is a very important example. And now I'm going to be honest with you. I wouldn't expect you to be able to do this, just based on what I've told you so far. But what I'm going to do is I'm going to walk through the way that you would attack a problem like this. And later, we're really going to nail down how to do this very precisely. But for now, we really are almost walking in the dark when it comes to instantaneous rate of change. Now, average rate of change is pretty concrete. It has a formula, f of b minus f of a divided by b minus a. But what about instantaneous rate of change? Okay, so our function here is x squared. So x squared looks something like this. It's a parabola. Here's x equals 1. Okay, and so how in the world are we going to figure out what the instantaneous rate of change is? And so the idea, remember, is to zoom in and pretend like when we zoom in close enough, the function is actually a line right here, and find the slope of that line. Now the way you do this, and actually this will be the way we do it later on, is we take 2 points pretty close to 1. So maybe we'll actually take 1 itself right here, and then just to illustrate the idea, we can take a point up here. And what I can do is I can draw the secant line between those 2 points, like that. Okay, so I have 2 points. I can draw the line connecting those 2 points. Now, if I let this point go closer and closer to this point, notice that I'm going to get secant lines that are more or less leveling out to be equal to the tangent line itself. Okay, so on the next slide, I'm going to show you a picture that I actually made on a computer that should make this point a little bit clearer. But this is the idea. We just want to look at secant lines around intervals that are really, really close to 1. Okay, so here's a picture of the situation we have going on here. In blue is the function x squared. And what I've done is I've plotted various secant lines over specific intervals. So in red, I have the secant line over this interval. Well, let me draw it in red. So the interval 1 to 2 in red right here. So you'll notice this is 2. Then in the slightly more orange color, I drew the secant line between 1 and 1.5. And then in the even lighter orange color, I drew the secant line between 1 and 1.25. Okay, so in general, here's the idea. I want to find the average rate of change over this interval. 1 to 1 plus some number. And so you see that here I set h, 1 plus h, to be 1. So 1 plus 1 is 2. Here h is 0.5. 1 plus 0.5 is 1.5. Here h is 0.25. So 1 plus 0.25 is 1.25. So I want to find the average rate of change over this interval. And notice that if I keep letting h get closer and closer and closer and closer to 0, these secant lines are getting closer and closer and closer to looking like the tangent line, which is drawn in black. Okay, so more or less this is step 1. So find the average rate of change of our function f of x equals x squared over this interval. And then the second step is let h get small. And I'm going to put get small here in quotes. Because remember, back on the introduction, I said that what we really need to do is we need to figure out how to zoom in and figure out what's happening on a very small scale. And in other words, we need to introduce this idea of a limit. And so what we really need to do here precisely is we need to take the limit as h goes to 0. But intuitively what we're doing is exactly what's in this picture. We're just finding a secant line, and then we're just letting that h, or the width of that interval, get really, really small, and let h approach 0. And what that's going to do is that's actually going to approach the tangent line. Now we'll see more of this a lot more precise later, but for now, what really needs to stick is this picture here. This secant, and that a tangent line really is somehow a limit, and I'll put that in quotes for now, a limit of secant lines. So let's actually see what it looks like when we do that. Okay, so recall that step 1 was to find the average rate of change of the function over the interval 1 to 1 plus h, where h I just want to think about as a small positive number. So h is just going to be some small positive number here. So this is the average rate of change of f over this interval, 1 to 1 plus h. And now I want to take h to be really small, but let's actually see what this is equal to first. So f of 1 plus h is just 1 plus h squared. And f of 1 is just 1 squared. And notice here, this is 1 plus h minus 1. Well, that's just h, because 1 minus 1 is 0, and I'm just left with h. Okay, now this is not very helpful. This is not very enlightening to me. So what I'm going to do is I'm going to FOIL out this term here. So I have that this is 1 plus 2h plus h squared, and then minus 1, all divided by h. Okay. Did I mention that algebra is the hardest part of calculus? We are going to start doing a lot of algebra. So notice again here that 1 minus 1 cancels, and we're left with 2h plus h squared divided by h. And this, now you got to be careful when you cancel things here, but notice that this term has an h, 2h. This term actually has two h's, it's h squared. And then the bottom has an h. And h is not equal to 0, okay? So then I can actually cancel one factor of h, so that kills the squared there, and I'm just left with 2 plus h, as long as h is a positive number. So the instantaneous rate of change, the average rate of change over this interval, 1 to 1 plus h, of this function is 2 plus h. Now you see that this is equal to 2 for small h. Okay, now this is an extremely imprecise step, so I don't want you to actually think that this is some sort of rigorous way to think about it. We're going to do this a lot more rigor later on. But if h is really, really small, so in other words, if I'm taking the average rate of change over an interval that's really, really close to 1, then it looks like the rate of change is getting close to 2. And so what we'll conclude is that the instantaneous rate of change is actually equal to 2. I mean, it actually is the truth that the instantaneous rate of change of this function at x equals 1 is 2. And here we're sort of seeing why that's the case. So this really is the instantaneous rate of change. And notice that a lot of what we did was just algebraic manipulation. And so you should probably get used to that because it's about to come in full force. Okay, so here we have a different function. G of x is equal to square root of x. So again, we want to find the average rate of change of g of x over these intervals. So the interval from 1 to 2, we'll do that. The interval from 1 to 1.5, and then the interval from 1 to 1 plus h. And here h we'll just think about as being a positive number. And later on, it will be no mystery while we're looking at an interval of this form. And in fact, in the last example, we saw why we might be interested in looking at the average rate of change of a function over an interval that looks like 1 to 1 plus h. Okay, so let's jump in. So from 1 to 2, the average rate of change is just g of 2 minus g of 1 divided by 2 minus 1. Okay, which is square root of 2 minus 1 over 2 minus 1, which is just square root of 2 minus 1. Okay, easy enough. Plug and chug. Then for 1 to 1.5, we have g of 1.5 minus g of 1 divided by 1.5 minus 1. Okay, so this is square root of 1.5 minus square root of 1 is just 1. And then we have 1.5 minus 1. Or in other words, it's just square root of 1.5 minus 1 over 0.5. And surely this has, just some, same in this case. These are just numbers. You can plug them in your calculator if you want. I'm not even going to bother simplifying them anymore. Okay, so what happens with 1 to 1 plus h? So we have g of 1 plus h minus g of 1 over 1 plus h minus 1. And the nice thing is the same thing is going to happen a lot here. I have 1 minus 1, so all I'm going to be left with is h. So I have square root of 1 plus h, that's g of 1 plus h, minus g of 1 is 1, all over h. Okay, and that's the average rate of change over this interval. Okay, so now we need to make a table of values for the average rate of change of g over the interval, okay, this last interval we looked at, 1 to 1 plus h, for values of h that are getting closer and closer to 0. And I actually already did that here, so I printed the table here. So here we have these values of h, and here recall that this was just the average rate of change of this function over this interval 1 to 1 plus h. And then for all these different values of h, I just plugged in those values into what we got. So remember, I think we got something like square root of 1 plus h minus 1 over h. Okay, so I just plugged in h using a calculator and got these numbers. But this is really cool because look what's happening. Is h gets closer and closer to 0, so this is a tenth, a hundredth, a thousandth, a 10,000th, a 100,000th. This is definitely getting very close to a number that I know. Okay, and C says, what does this table suggest is the instantaneous rate of change? Well, what is this table kind of begging you to say? I mean, you look at this and 0.4999999, that is so close to 0.5. I mean, you wouldn't even have to, you could just show this to anybody and say, what's the answer to this question? And you'd be tempted to say it's 0.5. And that's the truth. And this is what's going on here. The average rates of change for these values of h that are getting really small is approaching the instantaneous rate of change. And we're going to see this, and it's going to be very exciting. But you're just starting to see what's going on. We want to understand how a function is changing at an instant. And we understand how a function is changing over an interval. So we just let that interval get really, really, really close to the point, the instant that we want the rate of change, and then we guess, later we're not going to guess, but now we just guess that the instantaneous rate of change is 0.5. Okay, so we saw from our table in part B, and then we concluded in part C, that our instantaneous rate of change of this function at x equals 1 was 0.5. So can we get more evidence for this algebraically? And so remember that our instantaneous rate of change, I'm going to do that a lot. Our average rate of change of our function over this interval, 1 to 1 plus h, was square root of 1 plus h minus 1 divided by h. Okay, so I look at this and I don't see 0.5. Okay, if h gets really, really small, I mean, this is just not clear. And this is probably, again, an unfair question to ask you, which is why I'm going to do it for you. For now, later on, you'll be able to do some practice on your own. So how can we sort of see that the answer is 0.5 here? Well, this is a perfect time to introduce a very useful technique in calculus. And it's called multiplying by the conjugate. And it's going to happen a lot anytime you see a square root. So I just see the square root, and I really want to get rid of it. Okay. So basically what I'm going to do is I'm going to multiply the numerator and the denominator of this fraction by the same thing. And notice this is square root of 1 plus h minus 1. So I'm going to multiply by square root of 1 plus h plus 1. Now I multiply on the top by this factor. I also need to multiply at the bottom by this factor. Okay, and it's really okay if you are thinking right now, why in the world would I do this? Well, you do this because it's going to do something amazing. Okay, so let's think about what happens. Now, the reason I multiplied by this conjugate, changing this minus to a plus, is that this top numerator is actually a difference of squares. So it's something minus 1, and then that same something plus 1 multiplied together. So what this should end up being, in the numerator at least, is square root of 1 plus h squared minus 1 squared. So just remember, go back to those factorizations of difference of squares. This squared minus this squared is that minus 1 times that plus 1. And then in the denominator, well, I can't do anything with the denominator. It just is what it is, so to speak. Okay, so what happens in the numerator? Well, in the numerator, square root of 1 plus h squared is 1 plus h minus 1 all over this nasty thing. Okay, and now this is 1 minus 1, so those will cancel. Okay, and then I have an h divided by an h. And now remember, I'm thinking about h just being a small number, not equal to 0. So that cancels. So I'm actually just left with 1 over square root of 1 plus h plus 1. Now what happens is if h is really, really small, let's just set h to be 0. Then this becomes 1 over square root of 1 plus 1, which is 1/2. And now, all of a sudden, I'm going to put this equals in quotes because it's not really equal. All of a sudden, we see where 0.5 is coming from. It really is hidden in this complicated expression. We just had to do some manipulation or some algebra, right? The hardest part of this whole deal, to get to the answer of 1/2. And this is the instantaneous rate of change of this function, so the slope of the function at x equals 1.